This video is a brief review of laminar flow, which we covered in the previous lecture. So what we talked about was that developed flow, which is the flow where the velocity profile does not change with distance, has some distance over which it develops after the pipe transitions. And that distance is defined by entrance length. So for example, if the pipe changes from a tank into a pipe transition, then over the entrance length, the flow transitions from inviscid to viscous flow, and over this region, the flow becomes developed. And the definition of entrance length is different for pipe and parallel plates. It depends upon the diameter and the Reynolds number for that pipe, and also the inviscid core length is a fraction of the entrance length. In case of turbulent flow, the inviscid core length or the flow development length or the entrance length all depend upon diameter of the pipe, and they are a multiple of the diameter of the pipe. Moreover, we talked about the pressure drop in a pipe based upon elemental approach. And we found out that given a pipe of length L, in which the fluid is moving with velocity v and has a viscosity of mu, if the pipe's radiuses are naught or r sub 0, then the pressure drop delta P is given by this equation. We also found out that this pressure drop is related to the shear stress on the wall, which is tau sub 0. So this is the relationship between the pressure drop and how much shear stress is imposed by the boundary on the surface. We also talked about what the average velocity based upon the velocity profile would be, and what would be the head loss for a given length of pipe, which is L in this case, and for the velocity and given the diameter of the pipe. So based upon this, we also figured out that there's a friction factor called F, defined as the wall shear stress divided by 1/8 of rho v square. And using this equation, we were able to relate the head loss with the friction factor, length over diameter, and the velocity head, which is v square over 2g of the fluid flow. And we also learned that the friction factor for laminar flow, which we are talking about in this section, is 64 divided by the Reynolds number. Although we did the derivation for laminar flow in pipes, I talked about the laminar flow between parallel plates, and I told you that the equations are very similar to those for pipes, except with that in case of parallel plates we are using lowercase a, which is the small dimension or the distance between the two parallel plates. And the pressure drop over a length L of two parallel plates is similar. The only difference is the constant 12, and in place of the radius we are using the distance between the parallel plates. In a similar manner, the relationship between the pressure drop and the wall shear stress is similar. We are using thickness of parallel plates, the distance between parallel plates, and the velocity is 2/3 of the maximum velocity in the profile. And head loss again is related to the velocity, length, viscosity, and the specific weight and the distance between the two parallel plates. So depending upon the problem that you're dealing with, you would pick either set of equations based upon if you're using if you're trying to determine the pressure drop in a laminar flow in pipes or pressure drop for a laminar flow in parallel plates. These equations below, which is the friction factor, the head loss, and the friction factor for laminar flow, are same either whether you're using pipes or parallel plates. With that said, now Adam will take you through two problems. Problem 7.44 in your book, which is laminar flow in a pipe, and problem 7.56, which is laminar flow between parallel plates. And after this, we'll talk about the turbulent flow.